or the occupancy category. So which the seismic occupancy category is derived. So you have to consider in such a way that your short period response acceleration and the long period response acceleration, you have to take the critical. Whereas in this case, you see, so the building is located in zone 2, whereas your short period and long period values has been defined by the code, or there is also certain code says that we can calculate. There were formulas or predefined data based on the historical data. So when it is considered as the short period response acceleration, the building falls under category A, but on the long period, it falls under category C. So we need to consider the worst scenario where A is much safer, I mean to say, but the more you get like C and D is more critical, where your building falls under a zone where you must need to go for a seismic requirement. Design of seismic requirement is important. Yeah. And then comes to the building category. So now if you see the first step, we derived the site location, we derived the soil class, and then we derived the building zone category or the seismic category of that particular locality. Now comes to the building. So what kind of building we are going to construct? Is it a storage facility or is it a temporary structure? Maybe you see the project sites, until the project get finished, they put a temporary structure where all the engineers and site team will sit over there and execute the job. So these are temporary structures. Or is it a mall, or is it in a, so there are different. So as I mentioned that we are going to take an example of hospital. Hospital is one of the, which is again the healthcare facility. So what happens is that when any natural calamity happens, either it can be an earthquake or tsunami or whatever, or a fire accident, any structure can damage, but the life safety structures like hospitals or fire stations or any other life safety related structure should be intact, so that whatever the damage happened due to this natural calamity can be, the people will go to hospital, so they will have an access for life and healthcare. So this is the reason that it was given a category 4, which is the more important buildings falls under the higher categories. So now we had come to a conclusion that what are the different parameters or different stages we are assigning certain factors, or we are taking certain parameters into consideration and defining whether seismic requirement is required or not. So this is where your building has been constructed. Now then comes to the, so this until now whatever we discussed is same for your structural element and non-structural element. This is the general practice which is being followed across the countries or across the codes. So whatever the code you refer, only the notation changes, but the concept or the procedure remains the same. Then comes to the component importance factor. What is a component? So a component, in simple, I would say it can be a light which is fixed in your ceiling, or it can be a fan, or a ceiling fan, or it can be a unit. If you go to malls and all, you will have large units for AC supply or for water supply, which we call AHUs or fire pumps or chill water pumps. So there are different, these are all called components. Each element or each support which is getting fixed to the building, which is getting fixed to the attached to the main structure is called a component. So the component importance factor comes for the non-structural elements. So what is 1.5? I'll give you an example. So we went to a hospital. There is a reception area and there is also an ICU. So when you go to an ICU, so there is an air conditioning, and even in the reception also you got an air conditioning. During an earthquake or during some natural calamity, so the service which is going to the ICU should not get affected. So it should be designed in such a way that whatever the impact that comes due to the earthquake or due to the seismic activity should be resisted by that particular non-structural element, and it should not collapse, right? So that's the reason that it was given 1.5. but it can be the same air conditioning unit or whatever, or the same fan you can consider, which is installed in the reception area. So even if it get damaged or its functionality get damaged, assuming that the supply to that particular fan got obstructed because of this earthquake incident, is it going to create any damage over there? So it's not, right. So this is the concept which is being followed. So the building is subdivided into different categories based on the occupancy. So if it is a storeroom, hardly people goes, maybe once in a year, or it's not a group gathering which will happen in a storeroom. So the importance for that particular area inside the building is one. But if it is a conference room, or if it is an ICU, or if it is a room where multiple gatherings, or there is a designated service that has been, like if somebody is critical, which will get affected, like a ICU. So those has been classified as important rating of 1.5. I hope it is clear. So which is applicable to any building. So I just took an example of hospital, but you can relate it to any of the structures. So where we are defining, either it can be a mall, it can be your residential house, right? So based on this, we will arrive. So what is that again? This is related to seismic. So what does the code? What does the research says is that any service or any non-structural element which is being installed, or which is being attached to the structural concrete, which is having importance factor 1, doesn't need to have any seismic requirement. You don't need to provide an additional stiffness or additional support, or additional we call it anchoring or steel support, whatever you say. So it doesn't need to be seismically designed, as the whole structure is already designed. So these components or these can be exempted, right? But where the similar system, if it comes in a room which is having 1.5 importance factor, you must need to restrain it, or you must need to provide a element which should be seismically restrained. So hope this is clear. Let's go to the next point. So if you see the starting of my presentation, so we have only 4. I mean, you see a lot of different sizes or shapes, but when you come to the definition of the non-structural elements, you have only 4 types. The one which is related to electrical, which can be your lights, which can be your cables, your trays, trunking, whatever. So all falls under the electrical category. So there are some exceptions. This is also according to ACE, that there are 2 limitations. One is the weight parameter. Why weight parameter is that? So again, when we start the seismic design, or when we talk about seismic, the first thing comes in our mind is that the base shear. So the base shear defines everything. So it is weight times the base shear factor. So you get the more weight, so the oscillation is going to be more, the impact is going to be more, obviously. So there are weight limitations. That a simple example I'll give, and then I'll pass it on to the next services. As it's defined that electrical is 1, plumbing is 1, which carries your fresh water, drinking water, and the usage water. And HVAC is one topic that which will carry your air conditioning or chilled water, hot and cold water. And then last one is the fire services. If you go to a mall, or if you go to any this one where you see the red color pipes in the parking lots or in a hotel, where mostly you will see in multi-story buildings, all these red pipes are the fire pipes. Any fire accident happens, the whole building can get affected. So all services can get affected by the fire, but these fire services are designed to withstand the fire until like 1 hour, 2 hours, sometimes in 3 years. So it is again defined by the local civil defense or the fire department who is responsible for that. So that's a different topic. So if you take electrical as a example, that if any of the equipment or if any of the service in a building which is having a weight less than 15 kilogram per meter, or an individual unit, I'm talking about a cable which is running across the building. So if per meter weight is less than 15 kg, you can completely avoid providing a seismic brace. Or if there is any unit It can be a air conditioned unit, or it can be a light, or if you see the large scale structures, you will have a couple of equipments where you need to provide some supports. So such cases, if it's an individual unit, even though if it is less than 15 kg, so that you don't need to provide any seismic brace. So the idea is that, again, we are going back to the basic principle of base shear. So weight times your base shear factor, which defines your lateral force. So that's where this limitations has come. So this is where you can avoid. So why I'm explaining this is that, see, knowing that whether earthquake resistance or earthquake design is required for this building is very important. But at the same time, protecting the client or the contractor or whoever is responsible, the building owners, is also important. That way to avoid seismic and where it is really required is also one important aspect. That so we will not end up blindly providing the whole building with seismic supports, even though if it's not required. So which we call it as value engineering. So which is more important nowadays, that where there are a lot of challenges across the globe with geopolitics and the prices. As you see, there is a lot of things are going on with the tariffs right now. Yeah. So similarly for plumbing and HVAC, this is for the ducting. So I'm not going to go in deep. These are all there according to different standards and different codes. Then comes some special cases that where you have some equipments or some structures which are installed on the rooftop, or which is having certain, like it can be a chiller unit, or it can be a water tank, as an example, where you can relate it to any of the structures. So if these are installed on the rooftop, and the height from the roof slab level or whatever, so if it's less than 1.2 meters or 1200 millimeter, so you can avoid providing a seismic brace for it, or you doesn't need to design this for a seismic requirement, because this will not create a damage even though if there is a seismic activity, because the height is limited to 1.2 meter. So the impact which is getting created with this seismic activity will not be that. So this is again for the fire, which you can, I will be sharing this presentation also later on, so you can refer to it, because this is more into theories, which I want to show how this supports being installed or presented in a live project. So this is also one of the example of riser supports where the pipes are running, like if you have apartments or multi-storied buildings, where the pipes will be running through the shafts from the, say, 10th floor to the first floor or to the basement. So where you have huge hydraulic water pressure. These are freestanding for 30 to 40 meters height. So which creates a huge damage when there is a earthquake incident or any natural calamity. So such things has to be designed very carefully, that how to provide the restraints or how to provide the supports to control the damage, because these are the header pipes which actually supplies either your water, gas, whatever the service it is designated for. So these headers, if this gets damaged, so the whole structure's supply is going to get damaged. So always the importance factor for such components is going to be very crucial, and which is very important to do. On a structural wise, if you see, it's going to be a very minimal. If you go onto the sites, or if you go onto the the site team level, they say, yeah, it's just a pipe. It's my building is very big and it's very strong. My beams are very large, so it was designed, so nothing to worry. But the damage what gets created is not by the structure, but the elements which are getting attached to the structure. Yeah, so these are some of the exceptions or the must follow conditions which need to be followed. But this will be explained in a pictorial way where you can see that. So the red dotted line, what you see on the screen, is a pipe which is running across the building. So this is just a schematic explanation just to understand. So the arrows, what you see is you're restraining the pipe in both the directions sometimes, and sometimes it's only in one direction. So a simple example is that, let me take a pointer. Yeah, a simple example is that if you take this particular area, so this is the location where the pipe is taking 90-degree turn. So what happens, as we all see, and we study the hydraulics. So what happens is when there is a directional change in the pipe. So we see that there is a directional change of 45-degree or 60-degree or 90-degree. So what happens when there is a directional change in the water flow? So it creates an additional pressure, right? The force will get resolved into two components because the direction gets changed. So which we call it an elbow or a joint pressure in mechanical language, I would say. Actually, this is a joint of mechanical and structural subject. So if you see such locations, these elbows should be protected, means it should be designed for the hydrostatic pressure, as well as when assume that when the pipe is in operation, means when it is carrying full load of water and there is a seismic activity happen. And so it's the hydrostatic pressure is going to be very huge, and also it's close to like 12 bar pressure. That's a maximum that comes in a building. Either you can relate to any building. So that's a maximum 12 bar pressure which has to be designed. So a 12 bar pressure is huge, that it can burst off a complete one-story building. So it's that pressure. So when this pressure of water is coming and seismic activity or seismic incident and this impact of seismic is added on top of it, so all the piping or whatever will just get burst up when we are not restraining it from the all four sides in order to not to move. So that's the reason any of the elbows are strictly need to be protected with a minimum distance of 600 millimeter, say close to half a meter. So it must be protected or it must be seismically restrained. We will see some 3D pictures or 3D applications, how practically it looks like. So these are the different components. I hope now it is more clear, where you could see some couple of 3D images. So you get two types of supports. One is suspended supports. Other one is the floor mounted supports. So suspended, which are fixed to the bottom of the slab, where you will see, I mean, practically you will not see other than in the basements. So most of these services are concealed within the fall ceiling. So it will be below the slab and above the fall ceiling. So which will be hidden most of the times. And also some floor mounted supports, which are fixed basically on the rooftop. So as a good example is that our AC condensers are installed on the rooftop with some plugs and screws or some nails. So which is a very good example of floor mounted supports. So these are the typical restraints. What you can see that the arrows were presented just to give you the direction, whether it is lateral or longitudinal, which is perpendicular to the pipe. So this one is perpendicular to the pipe, which is called lateral support. And the one which is parallel to the pipe or structure, it is called longitudinal support. So it is just an example of pipes, but it can be an equipment. So there is no limitation for it unless it falls in a seismic requirement zone. So any of the building attachments has to have this kind of restraints. So where you can see this is two-way restraint, means both sides it has to be restrained. Mostly the tension members are designed to have both sides, because if this member is a tension members are nothing but solids. So if you take a solid rod, so I'm not talking about the hollow ones, it's a solid one. If it is 100% solid, mostly they are tension members, but still we limit to certain shapes of the profiles. So always the tension member should be on both the sides, because it cannot take compression. It's just like a spring. So whereas this is an example for ducting and trays, where you have AC services which passes through the ducting and cables which are laid on the cable trays. Also one-side applications. It all depends on the site accessibility and requirement. So there are a lot of parameters. Again, it falls under your fire categories. So there is so many parameters where you will decide whether you need to have two-way bracing or a one-way bracing or one-way restraint. So this is one-way restraint. What you can see is again the lateral and longitudinal with single and multiple services. We'll see some more pictures. So these are all a different applications with one-way, two-way, one-way applications. So coming to the fire, fire has a different importance. So it is just not like that because we were talking about the metal and again we are talking about the fire. So what happens when metal get in contact with the fire is the first one is who is going to get damaged is the metal itself. So this is again a tough challenge for the engineers that how do we handle metal with the fire. So keeping that any component or you see this some couple of metal items, what you see these components or this pipe, whatever you see on the screen other than the red one, which is the fire pipe, I mean, which carries the water. It's called as fire pipe because it's the purpose of this pipe is to arrest the fire when there is a fire accident. The sprinkles of water will come and fall on it to suppress the fire. So in this particular scenario, these all components, whatever you see, which is getting attached to this pipe, we should have a testing. So testing is again comes to universities. So in a small scale, in a large scale, you see that we get some certifications like CE marking, UL marking, or FM factory manual approval. So you see any medical equipment or any the blood sugar machines. These are all UL tested. You will see a mark called UL. So these components are also must be tested to UL to ensure that these are pre-tested. So generally what we do is that we take, how we design is that we take the beam as a simply supported or a cantilever beam and we apply certain load, get the reaction forces and analyze whether the moment capacity is passing or the axial force is passing. So we do theoretical calculations and prove that yes, this is fit to use. But here in the fire, along with the theory, you need to also prove practically that whether this seismic incident or this fire load is going, the fire effect is going to be withstand by these particular elements or not. So it's something like once in life situation that they will be practically creating a house. So installing all the possible different applications, all the critical applications or all the possible cases, and they will put a fire. So if anybody wants to access also, you can see that UL fire tests in YouTube or Google, you can type and you get so many videos which there was a live test which has been done and there are a lot of video references you can see. Right? So these are different applications which are again related to fire. As I said that fire become very common nowadays as the tall structures are coming up. So it's been that the importance will be given for the freshers, those who are coming to the market. So the regulations are being more advanced now, and it's going to be much more critical. The building can get up local municipality approval or the local authority approval without complying to a stringent fire specification. So these are the references of the code, what has been taken into consideration. So these are all the different codes you can refer to, where each service has its own sub clause, like how we have IS 800 or IS 456, where you have again special editions like SP 51. I'm not very sure. Sorry if I say any code name wrong. So there are some special backup documents which gives you more in detailed explanation about the codes, that how to calculate. There are even some live examples. So which is how these are all the codes were taken into consideration and whatever the data have presented. So there was a solid reference with these codes, and you can refer to this. So this is all what we discussed about the seismic and how it is important for a structural and non-structural application, and how this is being carried forward to the structures. So due to some limitations, I will not be able to present it how it's been implemented, but I'll be showing a project which I have been handling from last couple of years. So this is the hospital project which we were discussing. As until now, whatever the presentation you had seen is actually the one which was being constructed right now. So which is almost in a finishing stage. Where you can see this is the whole project. The one what you see on screen is close to 10,000 square meters of area. Yeah, you can just imagine how big the hospital or how big the building is. So why I shared this particular one is you can see there is some gray elements in this, and there are some uh, color which is in say sky blue or cyan or magenta color or say purple. So these are the different pipes or services which will run across the building. So which will run across the building, where you can see in 3D, right? You see, why I'm showing this is that it seems like very complicated. It's like a mesh which runs. You cannot name it. Wherever there is a room, there is going to be something which is going to come. Every room needs AC, every room needs water, every room needs electricity. So you just imagine how many services are going to come. By the way, the one what you see is only for the hot and cold water, which will run in hospital. So if you just add up all remaining services, it's going to be a web of pipes, cables, ducts. So you cannot imagine that how much it's going to be. So what happens in this scenario is there comes the clashes, right? So because as you see practically also, the one who construct the building, he will not do your plastering work or he will not do your tile work. You need to hire a separate mason to do the tile work, or for painter you get painter separately. So there are multiple departments or the multiple specialists who are going to get involved in order to craft the building, right? So in the secondary elements or the non-structural elements, so this is what exactly the one happens on a project scale. You will see a guy, a contractor or a team who is going to install your AC services, and then comes a new guy who will install your fire services, and one more guy is going to install your electrical services. So coordinating all these, you require as humans, it's our tend to do mistakes. So you cannot do this much of coordinations where you have huge number of services which are running across. So this is a rivet model or Navis model, we can say. I mean, it can be used in multiple platforms. It's just the tool, whatever the tool we adopt, we can create such models. So the current situation is that it is called BIM, again building information model. So all the services has been incorporated into such models, and you also might have come across. Sorry for the interruption. You also might have come across the word called chatbot, right? So likewise, these are the AI applications. Actually, we were using a couple of them now, but due to some security reasons and which is in development stage, I cannot be able to present you a live case that how it detects the building clashes or the service clashes. So where a pipe is coming in clashing with a tray, which was not observed on the drawings because there are thousands and thousands of drawings for a project. So identifying the clash on a 2D AutoCAD drawing is much, I would say, impossible. So there comes this 3D integration that everything is incorporated into 3D. So 3D is nothing but the one what you see actually on the ground. So where you can see from all three dimensions and then easily forecast where is the clash. So even to more adapt. So if I give this to an engineer to check where is the clash, he's going to spend maybe a month time to check each service one by one, then identify where is the clash. So these AI applications has come in such a way that you just give this model as an input and it runs the analysis. It runs the analysis and it will do all the clash detection and it will give you a report that in which location, which size of the tray or which particular element is getting clash with what is the tolerance they have. So you can define a tolerance like, the gap to gap between the services or gap to gap between the elements. So it's going to give you a very nice report, and it's easy for us. Say you got 10 clashes, and click on the clash, and it will take you to that particular location, and then you can change your model. So it's become that easy, and it's going to be much more advanced as you see in your daily life now. I think most of us started using AI, and it's going to be much more advanced in construction industry also, which is at a very slow pace. But the usage and the accuracy of work is going to get impact rapidly with these AI tools. So this is one of the core thing that I want to present, and I think now we are at, I don't know how it's been. So if you have any questions or clarifications, I request Mr. Durga Prasad to give access so that you can put your questions in the chat box. Or if you have any thing, you can also ask directly to me.
Yes, I'm unmuting all the participants actually. So the participants, those who have any queries, they can proceed with queries now.
Any questions?
I once again request all the participants, please proceed with the queries.
There was a question from Mr. Jitendra. Do we have any Indian standard for the MEP work like ASCE have? Yes, of course. We do have Indian codes where it defines what kind of supports that need to be provided. I'm not very sure about the code, but you can refer to IS 800, which is mostly related to the steel structures, where you get a separate chapter which is for design of non-structural elements. So there you get a lot of references, and again for MEP where we talk, it's like a vast subject because each has its own discipline, like plumbing, firefighting, HVAC. So each has its own codes and standards. Maybe you can Google it or find out that which standard is related to which. But there are codes which are available. So it's just the identification of the number, which code is related to what aspect. Any other questions or? There was a question from Sai Kumar Reddy, why we are providing seismic bracing in non-structural elements. This is what I had presented. See, non-structural element is what actually creates the damage than a structural element. Your structural elements are beams and columns, which are, we call it the skeleton of the structure itself. The non-structural element is that your interior finishes, whatever you can call it, or your equipment, furniture, all these are non-structural elements. So when there is an earthquake incident, assume that you are sleeping in your bedroom, all of a sudden the fan has just broken down due to seismic. It started oscillating like a pendulum and it just fallen down. So it can cause somebody's life. So to ensure that, you need to have the component. So generally you use some metal hook or something, or which is in a structural terms it's called the anchoring of the ceiling fan or the unit. So which should have a provision to provide a seismic, and there will be a safety attachment to that. So even if it collapse, it will just hang there. It will not fall off for any seismic activity. So that's the reason that you need to have a seismic requirement or seismic design for non-structural elements as well. Any more questions, or shall we wind up?
Yeah, sir. Hello. This is Jitendra. Am I
Yes,
audible?
Jitendra. Yes, yes. Please go ahead.
Just one last question I want to have. I'm from actually Rajasthan, and I'm teaching here in an engineering college. And the one thing that I saw in your presentation that you were using Navisworks for that all the things and like that. Right now here we emphasize more on teaching students like Stud Pro, ETABS, and with the basics of AutoCAD. So do you think we need to approach for the Naviswork kind of softwares also? Is there any demand right now? Like we need to pay attention to the Naviswork also? Because I have heard about this software many times before.
Mhm. See, on an academic level, see, software is, there are pros and cons. Actually, what I suggest is that when you have a tool, we will not go much deep into the technical aspect. Nowadays, the situation has become is like, if you know software very well, or either it can be a STAD or it can be ETABS or SAP, whatever, there are a number of tools. So people are more used for software, and if you give a small simply supported beam and ask him to design whether this section is going to pass for this load or not. So we are not remembering the formulas of what is the bending moment, what is the shear force, what is Carnot method, how this formula is arrived. Because the software, you just put two nodes and attach a beam and apply a load, it says it pass. So on an academic level, it is very important to that he should know the concepts. Yeah, in his third year or final year, he should apply this concept what he learned in the classroom to the subject, and then simplify the things. But it is becoming reverse. It's a ulta that people are more. If there is no software, then he become helpless. That I may not be able to know how do I do this design. And coming to this software knowledge, yes, having software knowledge is very important, but there is no limitation, to be honest. It's also become like, now how the things has come up. So you can design in any software. It also creates a confusion to the students that some says I will learn STAT, some other says I will learn ETABS, and some ex-person comes from the industry and says you learn SAP, it is very good. So, but end of the day, the ultimate aim of all these things is when you are strong with your basics, when you are strong with your academics. So these are just the tools. So even if tomorrow there is no tool, you can. It's just a matter of time. You spend 2 hours more time, and since you don't have a software tool, and you do all the manual calculations. But on an academics level, I suggest not to include that in the first couple of years. You can direct them, and it's up to the industry. And anyway, see, once these are the tools that it can, if you fully concentrate, it's a matter of weeks or months time. It's not going to take years to learn these softwares. So it's just the interface is different, but end of the day, all the software does the same job, right? So anyway, once they get into the work, they are going to learn this. They have to learn this. How they are going to learn the subjects to pass the exams. Any more questions? I hope, Mr. Jitendra, it's clear.
Yes, sir. Thank you so much, sir.
Thank you.
Yeah, it's great to be interactive, Mr. Jitendra. Thank you. Thank you for asking your questions. Are there any other questions? Nothing on the short box. Okay. Raisha, if possible, we'll wind up the session. Let me give the vote of thanks.
Yeah.
On behalf of Space Institute of Technology and Sciences and Department of Civil Engineering, it's my privilege and honor to extend a heartfelt vote of thanks to our esteemed guest, Rajesh Thallapaneni, for gracing today's event with presence and for sharing his invaluable sights with us. I wish to place a record of our appreciation for your dedication and commitment towards guiding and mentoring the younger generation. Your words have motivated us. Thank you for being a part of this program. We are very, very happy that you have taken your time to present your sights on this particular topic. Thank you very much. Sincerely thank once again Mr. Rajesh Thallapaneni for valuable contribution for the success of this program. We're looking forward to much more interactions with you in the future. And to all the participants here, the best of surprise. We too both, me and Mr. Rajesh are the batchmates are BTech. We have studied BTech and we are both our friends. We have traveled around 4 years. And it was great to see this in such heights. Thank you, Rajesh. Thank you for considering us when you have asked. And thank you on behalf of Space Institute of Technology and Sciences and all the participants. Thank you very much.
Yeah. Thank you so much. And I would like to thank the Pace Institute and all the participants first, and Pace Institute of Technology who has took me on board for this event, and special thanks to Mr. Durga Prasad and the HODs of Civil Engineering Department. Thank you so much.